Hey everyone, in this video we're going to learn how to graph exponential functions with transformations. So we're going to build off the basic exponential functions we graphed in the previous video by applying transformations to our graphs. Our directions: graph the following exponential functions by determining the transformation that is being performed to the parent exponential function. Determine the domain, range, and horizontal asymptote. Important to note here, there is not a single parent exponential function. It's going to change from problem to problem. So for instance, y equals 2 to the x is not the parent function for every exponential graph. It's going to be based on the function they gave us. So in this first example, we have y equals 1/9 times 3 to the x. So if we look at the base of the exponential function, it's base 3. So our parent function is going to be the exponential function with a base of 3. Okay, so we have y equals 1/9 times 3 to the x. Our parent function is y equals 3 to the x. Now we need to identify our scale factor. So the 1/9 coefficient we can divide to the other side. So y divided by 1/9 equals 3 to the x. Since we're dividing y in our equation, we have a scaling, and our scale factor will be 1/1/9, right? Nothing happening to the x. So we'll create a table of values. So we'll start with our parent function, y equals 3 to the x, and create our table of values. So x and y, so -2, -1, 0, 1, 2. Now because I notice that we're going to be multiplying the y values by 1/9, I'm going to include a few more positive x values that might be a little bit larger than normally fit on the graph, but possibly when we multiply by 1/9 will fit. So 3, 4, that should be good. Okay, so 3 to the 0 is 1, 3 to the first is 3, 3 squared is 9, 3 cubed is 27, 3 to the fourth is 81, 3 to the negative first is 1/3, 3 to the negative second is 1/9. So now we're going to apply our scale factor to find our new set of points. So multiply every x by 1, y by 1/9. So -2, 1 over 81, -1, 1 over 27, 0, 1/9, 1, 1/3, 2, 1, 3, 3, 4, 9. Okay, we don't have to plot all of these points, but we can plot a bunch of them. So we'll start with 2, 1. So 2, 1, and then we had 3, 3, we had 4, 9, 1, 1/3, and 0, 1/9. Now after that, it would get tough to estimate, so I'll stop there. So we can connect the 5 points that we plotted. So we go along the x-axis through our points. And there we have the graph of y equals 1/9 times 3 to the x. Now they ask us to find domain, range, and horizontal asymptote. Okay, so our domain, as we go left to right, every x value works, so that's all reals, -infinity to infinity. Our range, the fractions get smaller and smaller, but never reach 0. So 0 to infinity, not including 0. And our horizontal asymptote, which I'll abbreviate HA, well, the y values get closer and closer to 0. So our horizontal asymptote is y equals 0. So there we have our first exponential graph that's been transformed, in this case with a scaling. Same directions, our next function is y equals 2 to the x plus 3 minus 5. So first we'll move the -5 over, so y plus 5 equals 2 to the x plus 3. So our parent function, well, the base is 2, so y equals 2 to the x. Now we get to bring up another important idea. Normally when we're talking about transformations that are occurring to the x value, whether they're scalings, reflections, or translations, we're always saying that they're occurring inside the parent function, where x is located. Now, for an exponential function, the exponent is the inside part. So right here, this x plus 3, that's what we want to think of as inside the parent function. So anything that's happening up in the exponent is occurring to x. So in this case, we have x plus 3 and y plus 5. So we have a translation. If the equation is adding 3 to x, we're going to do the opposite. We're going to subtract 3. And adding 5 to y, we're going to subtract 5. So now we need a set of points to graph, but we'll start by creating our table of values for our parent function. So -3, -2, -1, 0, 1, 2, 3. 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, 2 cubed is 8, 2 to the negative first is 1/2, 2 to the negative second is 1/4, 2 to the negative third is 1/8. Now we're going to use that translation to get our new set of points. So we have, we're going to subtract 3 from every x and 5 from every y. So we have -6, and then 1/8 minus 5, that's going to be -4 7/8. And we can write it as an improper fraction. Right? We're trying to plot points. And then we're going to have -5, 1/4 minus 5, so that's -4 3/4. -1 minus 3, so that's -4. 1/2 minus 5, so that's -4 1/2. Then we have -3, -4, -2, -3, -1, -1, and 0, 3. So we'll plot our points. So we'll start with 0, 3, 0, 1, 2, 3, and work our way back. So -1, -1, -2, -3, -3, -4, and then -4, -4 1/2, and -5, -4 3/4, and then -4 7/8. Okay, so it looks like we're getting closer and closer to -5, but we'll never quite get there. Okay, so we go along -5 through our points, up through our points, and there we have our graph. Now, normally the x-axis is the horizontal asymptote, but in this case, we moved everything down 5. Well, that includes the horizontal asymptote, so if I wanted to, I can put a dashed line in here just to visualize what that horizontal asymptote would look like. And here we have y equals 2 to the x plus 3 minus 5. Okay, so domain, that's all real still. Our range, well, the values get closer and closer to -5, but aren't ever going to get there. So our range goes from -5 to infinity, but does not include -5. And our horizontal asymptote, which I'll abbreviate HA again, is y equals -5. So when we have a vertical translation, when we're moving the graph up or down, the horizontal asymptote is also going to move up or down. So we've seen an example with a scaling, and we've seen an example with a translation. Next, we have y equals -1 times 1/3 to the x divided by 4. Okay, so first identifying that parent function. So the base here is 1/3. So our parent function is y equals 1/3 to the x. Now we want to rewrite our function to identify that scale factor. So we can divide both sides by -1. So y divided by -1 equals 1/3 to the x divided by 4. So again, remember that idea that the exponent, whatever's happening up in the exponent, is happening to x. That's our inside for this type of function. So we have a scale factor because we're dividing x and we're dividing y. Okay, so our scale factor here, is multiply x by 4, right, the opposite of dividing, and multiply y by -1. So that means if we had to describe this, we'd have a horizontal stretch by a factor of 4, and we're going to wind up reflecting over the x-axis. Okay, so let's see what that looks like. First, we need to create our table of values. Okay, so we have x, and we have y. So we'll go -2, -1, 0, 1, 2. We can always add points if we need, but we're multiplying x by 4, so I'm not going to go too crazy with this table of values. So 1/3 to the 0 is 1, 1/3 to the first is 1/3, 1/3 to the second is 1/9, 1/3 to the negative first is 3, 1/3 to the negative second is 9. Okay, so we are going to scale everything by a factor of 4, -1 to create our new set of points. So multiply every x by 4, y by -1. So we get -8, -9, -4, -3, 0, 1, 0, -1 rather, 4, -1/3, and 8, -1/9. Okay, so let's plot these points. So -8, -9, all the way down there. -4, 1, 2, 3, 4, -1, 2, 3, 0, -1, 4, -1/3, and 8, -1/9. Okay, so it definitely looks like that graph's been stretched out horizontally. So now let's see if I can connect these points nicely. Okay, so going through our points and then going along the x-axis. So there we have our graph. That's y equals -1 times 1/3 to the x over 4. Domain. So that's all reals, -infinity to infinity. Our range, well, because we reflected over the x-axis, our range is now going from -infinity all the way up to 0. So our range is -infinity to 0. And our horizontal asymptote, well, the values are still getting closer and closer to 0, just from the other side, from the negative side now. So the horizontal asymptote is still y equals 0. Okay, so here we saw another scaling, but this time it incorporated a reflection as well. Next, y equals 2 to the -x plus 1. So our parent function, the base is 2, so y equals 2 to the x is the parent function for this example. Now we need to rewrite this, so y minus 1 equals 2 to the x divided by -1. So in this case, we have both a scaling and a translation. We're dividing and subtracting in the equation. Okay, so our scale factor, we always like to identify that first. We're dividing x by -1, so we're going to multiply x by -1 and y by 1. And then we're going to follow that with a translation, nothing being added to x, so 0 for x. And if we're subtracting 1 from y, we're going to add 1 to y. Okay, so we have to do this in a two-step process. Okay, so let's start with our parent function. So -3, -2, -1, 0, 1, 2, 3. So we have 2 to the 0 is 1, 2 to the first is 2, 4, 8, 2 to the negative first is 1/2, 2 to the negative second is 1/4, and 1/8. Okay, so we'll start with that scale factor of -1, 1. Okay, multiply all those x values by -1, y stays the same. So 3, 1/8, 2, 1/4, 1, 1/2, 0, 1, -1, 2, -2, 4, -3, 8. And remember, what happens when we're negating the x? We're reflecting over the y-axis, right? So all the points that had negative x values now have positive x values, and vice versa. And then we're going to follow that up with a translation of 0, 1. So we're going to add 1 to all of the y values. So 3, and then 1 1/8, 2, 1 1/4, 1, 1 1/2, 0, 2, -1, 3, -2, 5, -3, 9. Okay, so let's plot our points. So -3, 9, -3, 9, -2, 1, 2, 3, 4, 5, -1, 3, 0, 2, 1, 1 1/2, 2, 1 1/4, 1 1/8. Okay, so I'll work backwards again. So we're going to go along y equals 1, up through our points. So there we have our graph of y equals 2 to the negative x plus 1. Now notice, we had a vertical translation, right? So that horizontal asymptote moved up with it. Right? So if I wanted to put it in so we could see it, right, we have that horizontal asymptote right across at y equals 1. So our domain is all reals, -infinity to infinity. Our range, well, everything moved up 1, so we're now going 1 to infinity. And the horizontal asymptote, as we sketched it in there, is y equals 1. Okay, so we had two transformations here. We had a reflection over the y-axis, and then we moved everything up 1, and then the resulting graph is drawn, as well as the domain, range, and horizontal asymptote. Write the equation of y equals 5 to the x after a horizontal compression by a factor of 1/2. Okay, so that means our scaling would be 1/2, 1. So then in our function, in our equation, if we're multiplying x by 1/2, we're going to divide x by 1/2 up in the exponent, right? Because that's the new inside of the parent function. So if we clean that up, that's going to be y equals 5 to the, well, x divided by 1/2 is the same as 2x. So y equals 5 to the 2x is our equation. Write the equation of y equals 3/4 to the x after a reflection over the x-axis and a shift right 7. Okay, our reflection, we're going to treat as a scaling. So if we're reflecting over the x, we're negating the y. And then we're going to follow that up, shift right 7. So that's a translation of 7, 0. Okay, so first we'll apply our scaling. So we're going to divide y by -1. And that's equal to 3/4x. Then we're going to take that and follow it up with this translation. So y over -1 equals 3/4. So if we're adding 7 to x, we're going to subtract 7 in the equation. And remember, x is up in the exponent. So our exponent now becomes x minus 7. And in y equals form, we have y equals -1 times 3/4 to the x minus 7. And there we have our equation after a reflection over the x-axis and a shift right 7. Write an exponential function for the following graph. Well, we've wrote exponential functions from table, so what I would do is create a table of values based off the points in our graph. So x, y, so -2, 9, -1, 3, 0, 1, And then these would be estimates. But if I keep the pattern going, I'm dividing by 3 each time. So 1 1/3, 2 1/9 seems like what the value should be. Okay, so first let's figure out what the base of the function should be. What am I multiplying as x goes up? Multiplying by 1/3, right? Times 1/3. That's how we got these values. Okay, so the base of our function is 1/3. And then what's that initial value? If I plug 0 in, right, let's make this a. If we plug 0 in, we get 1. So 1 equals a times 1/3 to the 0. 1/3 to the 0 is just 1, so 1 equals a. So our equation is y equals 1 times 1/3 to the x, or just 1/3 to the x. We don't need that 1 in front. Now we're not going to get crazy with writing equations of graphs because they can get pretty hard to identify pretty quickly. If we do, it's going to be a basic exponential function that we're looking for you to identify the base. That's going to be the main part here. So our last 2 examples are thinking questions. Our first, when graphing exponential functions, Noah noticed that the graphs of 2 different functions given below were the same. Use the properties of exponents to show why this is true. So our 2 functions that Noah noticed were the same are y equals 3 to the negative x and y equals 1/3 to the x. So I'm going to start with y equals 1/3 to the x, although it doesn't matter which one you start with. So y equals 1/3 to the x. So we want to use the properties of exponents to try to show that this is the same as this. Okay, well, 1/3, I can rewrite that as 3 to the negative first to the x. Right, a negative exponent reciprocates. So if I have 1/3, I can rewrite that as 3 to the negative first. Now I have a base raised to an exponent to another exponent. And the properties of exponents tell me I can multiply these exponents together. So that's going to be 3 to the negative x, which is exactly the other function that Noah noticed was the same as 1/3 to the x. Now I said it didn't matter where you started. So if you started with 3 to the negative x, your steps would just look to be in the reverse order. You would have started by rewriting it as 3 to the negative first to the x. Maybe that's a little harder to notice, but then you would finish with 1/3 to the x. So what is this showing? This is showing that a basic exponential function, 1/3 to the x, and a transformed exponential function, 3 to the negative x, which is a reflection of 3 to the x over the y-axis, would produce the same exact graph. And we're able to show that algebraically with our properties of exponents. Our last example, similar. When graphing exponential functions, Sam noticed that the graphs of 2 different functions, given below, were the same. Use the properties of exponents to show why this is true. So the 2 that Sam noticed were the same are y equals 5 to the x minus 3 and y equals 1 over 125 times 5 to the x. Again, it doesn't matter which one we start with, but let's start with y equals 1 over 125 times 5 to the x. So the only reason for a preference is if you see a way to manipulate one of these functions over the other, I would start with the one you notice what you can do. So now, 125, I can write that as 5 cubed. So I have 1 over 5 cubed times 5 to the x, which I can make a single fraction as 5 to the x over 5 to the third. Now, if we remember our properties of exponents, when we're dividing 2 terms with the same base and different exponents, we subtract the exponents, so it would be 5 to the x minus 3, which is exactly the other function that Sam noticed was the same as the one we started with, 1 divided by 125 times 5 to the x. And again, what we're trying to show is 2 different transformations. In this case, we have a vertical compression. In this case, we're moving the graph to the right 3. 2 very different transformations produce the same graph with exponential functions. And we showed it algebraically. Okay, so the key concepts here. First, tying our transformations into exponential functions. And then second, using properties of exponents to show why some transformations of exponential functions produce the same graph. Now, go and practice these ideas before moving on to the next video. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.